Hello class. This lesson is part of a sequence on solution stoichiometry. In our last lesson, we discussed neutralization calculations and acid and base titrations. Titration is the process of adding a volume and known molarity of either acid or base to an unknown sample of the opposite. So if I add a known amount of acid to base of an unknown molarity, I can then determine that molarity of my unknown sample. I could also use it to provide analysis of other things such as standardized solutions. Let's read through this example in exercise 12, and then we'll discuss why we need to standardize solutions. So it says a student carries out an experiment to standardize, which means determine the exact concentration of a sodium hydroxide solution. To do this, the student weighs out a 1.3009 gram sample of potassium hydrogen phthalate, which is KHC8H4O4, and it's often abbreviated KHP. KHP, which has a molar mass of 204.22 grams per mole, has one acidic hydrogen. The student dissolves the KHP in distilled water, adds phenolphthalein as an indicator, and titrates the resulting solution with the sodium hydroxide solution to the phenolphthalein endpoint. The difference between the final and initial burette readings indicates that 41.20 milliliters of the sodium hydroxide solution is required to react exactly with 1.3009 grams of KHP. Calculate the concentration of the sodium hydroxide solution. So first, let's discuss why we need to do this. There is a vocabulary term that describes the nature of solid sodium hydroxide when we go to measure it. The term is hygroscopic. Sodium hydroxide is hygroscopic, which means that in the solid form, it absorbs water from the air. This presents a problem because when you go to measure an exact amount of sodium hydroxide sodium hydroxide solid, you end up measuring both sodium hydroxide and some small percentage of water. As a result, it doesn't matter how accurate your scale is when you measure your sodium hydroxide. When you go to make your solution of sodium hydroxide, it is going to be slightly off due to the extra water that has already been absorbed by the solid. So as a result, we need to standardize our sodium hydroxide solutions to find out their exact concentrations. This process is something that you will actually do in lab at some point during the year. You will measure a very, very accurate amount of KHP. You can see that on this particular scale, they have 5 significant figures, 1.3009, which is very, very accurate. I don't know if we have a scale quite that accurate, but we're going to get as close as we can. By having a really accurate amount of KHP and neutralizing it with your sodium hydroxide, we can determine very accurately what concentration of sodium hydroxide we have. As a result of some amount of water being added to our sodium hydroxide pellets through the air, our molarity of sodium hydroxide will be to some degree lower than what we predict it to be. So that is the purpose for doing this experiment. It allows us to figure out an exact concentration of a hygroscopic solution. So the important information here, they tell us that we are dealing with one acidic hydrogen. So if we're thinking about a net ionic equation, what that really means is that the H plus is our KHP, and the OH minus comes from our NaOH, and we are forming water. So we're trying to figure out the exact number of moles of each. We have the exact moles of H plus. Therefore, to neutralize it, we'll know the exact moles of OH minus, and then we can figure out the molarity from there. So first things first, let's convert our grams of KHP to moles. And again, significant figures are going to matter here a lot because we're trying to be as accurate as possible. So, technicalities. Here we go. 1.3009 divided by 204.22. And then I get 0.0063701 if I'm rounding. I shouldn't round until the very end of my problem. You know what? You're right. I should not end to the very end of my problem. Let's leave that whole thing in the calculator. Moles of KHP. And since that's moles of KHP, that's going to be equal to moles of OH. 0.006370091 moles KHP times 1 mole of H plus for every 1 mole of KHP. And then I also know it's a neutralization reaction, so 1 mole of H plus will neutralize 1 mole of OH minus, and I can figure out exactly how many moles of OH minus I need. I also know that 1 mole of OH minus is going to be equal to 1 mole of NaOH because I have 1 mole of OH per mole of NaOH. Through this stoichiometry, I've canceled moles of KHP, moles of H+, moles of OH, and I'll be left with moles of sodium hydroxide in my final answer. And you've noticed that all of these fractions are basically just multiplying by 1 over 1. So hopefully we recognize that our original answer of 0.00637000911 moles is equal to our moles of NaOH. So then I need to divide my moles by my volume to get my concentration. So my volume is 41.20 milliliters, and I have to divide this by 1,000 milliliters to convert it to liters, because a concentration is always reported in moles per liters. So I'm going to divide my answer and open parentheses 41.20 divided by 1,000, close parentheses. And I get a molarity of 0.1546, yada, yada, yada. However, I need to pay attention to my significant figures. I had 5 significant figures with my KHP, but 4 significant figures with my volume. So 1546 molar NaOH would be my final answer for 4 significant figures. Okay. And that's really all there is to it. It looks like a very intimidating problem from the amount of information given to you, but once we've explained the process, hopefully you see it's relatively straightforward. It's just doing some gram to mole conversions and then determining a molarity. Go ahead and try these two for yourself. Okay, it is time to discuss the last type of reaction, and this is called an oxidation reduction reaction, or redox for short. These reactions involve the transfer of electrons from the reactants to the products. There are some ways we can remember this. Oil rig is one way you can remember the process. Oxidation is loss, reduction is gain. And when we're talking about loss and gain, of course, we're talking about of the electrons. So oxidation is when we lose electrons and result in an increase in charge. When something is oxidized, it becomes more positive. When we have reduction, we have a gain of electrons and a reduction in charge, aka it becomes more negative. So for instance, if I have a charge of 0 and I am neutral and I end up with a charge of +1, that is oxidation. If I have a charge of, say, +2 and end up with a charge of +1, the charge has gone down or been reduced, and therefore it is a reduction. We also have the term oxidation state or oxidation number, and this is very similar to the idea of assigning a charge on an atom. So we do have some rules for assigning oxidation states, and we do need to memorize them. The oxidation state of an atom in an element is 0. So if you have an element such as sodium, or maybe a diatomic element like oxygen gas, O2, or even another pure substance like mercury as a liquid, all of those things have no charge, and therefore their oxidation states are 0. That only works for elemental states. The oxidation state of a monatomic ion is the same as its charge. Monatomic meaning single atom, so Na+, Cl-, etc. The oxidation state for Na+ would be 1+. The oxidation state for Cl- would be 1-. When fluorine is part of a compound, it is always assigned an oxidation state of -1. Oxygen is usually assigned an oxidation state of -2 when it is in a compound. There are some exceptions. The peroxide ion, which is a polyatomic ion, is O2 with a 2- charge. Each oxygen is a -1 oxidation state. There's also an example for OF2, where oxygen is +2 since F has to be -1. The hydrogen is assigned an oxidation state of +1 when it is in a covalent compound with nonmetals. There is an exception. Metal hydrides, for instance, have an oxidation state of -1, and this is because H is at the end of the formula, and the metals usually have a set oxidation state per Rule 2 when we said that the monatomic ion is the same as its charge. In bold, and it's the last step or rule for oxidation states, the sum of oxidation states must add up to the overall charge. So if something is electrically neutral, the sum of the oxidation states is 0. For polyatomic ions, the sum of the oxidation states is equal to the charge. So let's find some oxidation states in the following atoms. Here we have CO2. Oxygen, as we said, is a -2. But I have 2 oxygens. So here's for oxygen number 1, here's for oxygen number 2. And carbon, we do not know carbon's oxidation state yet, but we see that this is a neutral compound, so when I add these together, I have to get 0 to make up my CO2. If I have a total of -2 and -2, that means -4. To get back to 0, carbon must have an oxidation state of a +4. So C is a +4, and each oxygen is -2. Let's try this with SF6. Well, with SF6, each F has to be a -1 each, and there is 6 of them. So overall, we have -6 being contributed by my fluorine because I have 6 fluorines present. Sulfur must be a +6 in order to get SF6 down to 0. It's a little bit trickier when you're doing a polyatomic ion such as NO3-, but we'll take the time to look at it. So I have N, and then each O contributes a -2. The problem is, with NO3, it has a 1- charge, so the answer actually needs to add up to -1. So if each oxygen contributes -2, that means overall -6 is being contributed by my oxygens. Nitrogen has to be a +5 because 5 and -6 makes -1, which is my charge of nitrate. So nitrogen has to be a +5, and oxygen has to be -2 for each. In You Try It Set 13, there are plenty of practice problems with assigning oxidation states. We'll talk about why assigning oxidation states matter when you come back from some practice. Welcome back. Here we go. Here is why oxidation states matter. We need to be able to identify if a substance has been reduced or oxidized in a redox reaction. So to do this, we first need to look at the oxidation states of the reactants and compare them to the oxidation states of the products. As I showed you before, we have this idea that if the charge increases, then the substance is oxidized. If the charge decreases, then the substance is being reduced. So in this first example, our reactants are both elements because Cl2 is diatomic. So these each have oxidation states of 0. And then they form an ionic compound. When we are forming an ionic compound, what we're really looking at is Na plus and Cl minus. So the charge increases for sodium and decreases for chlorine. If the charge is increasing, that means Na is oxidized. So oxidation is a loss of an electron. If I lose an electron, I become positive. If I gain an electron, I become negative. Chlorine gained an electron, so it is reduced. The charge went from 0 to -1. That is a smaller charge. Now, what we'll get to in the electrochemistry unit is a discussion of half reactions. So, quite literally, what is happening here is that sodium is losing an electron, so its products are Na plus, and then 1 mole of electrons, E minus. E is a product, meaning it is being lost or given off. With chlorine, you end up with a mole of electrons per chlorine, so 2 E minus are being added, electrons are being gained to become negative, and you end up with 2 moles of Cl minus ions. We'll talk about how to balance these half reactions in another lesson when we get to electrochemistry. But that is a little teaser so you understand what I mean by electrons being lost or gained. Here, electron is lost, which means it's a product. Here, electron is gained, so it is a reactant. All right, let's try a couple of more. So with oxygen, elemental oxygen is 0. We said that hydrogen will assume when it's in a covalent compound, it will have a +1 charge. If each of these hydrogens are +1, then carbon has to be -4. Here, each of these oxygens is -2, so carbon has to be a +4. -2 -2 gives me +4. And then here, -2 for my oxygens, and each hydrogen has to be +1. I guess technically I should write, I've got 4 +1s over here for my hydrogens. So again, we're going to track the elements. C from reactants to products goes from -4 to +4, which means that it had to lose electrons to become positive, which means this is oxidized. So carbon is oxidized. Hydrogen starts out as +1 and stays as +1, so there's no change. But oxygen goes from 0 to -2. Oxygen goes from 0 to -2. That means gaining electrons. Therefore, oxygen is reduced. Let's do one more, and then we'll try some on our own. Elemental aluminum is 0. Elemental iodine is 0. Here, I end up with a +3 for aluminum, and each iodine is a -1 because it's a halogen. That you just have to look at in terms of charges, right? Al(I3) would split up into Al3+ and 3 I-. So that's where we're getting that from. Here, it's relatively easy to see that since aluminum went up in charge from 0 to 3+, it is being oxidized, and iodine goes from 0 to -1. It is being reduced. All right, that is all for solution stoichiometry. You've got You Try It set 14, and that is a wrap on this unit. We'll see you in the next one.